This is a lesson on the basic principles of quantum mechanics in a unit on modern physics. I wanted to start this lesson by covering what we know about light, some properties of light, which you can go back and look at those videos for. But just to highlight that the speed of light we know as a given value, it's constant, and also that there's a wave nature to light where we relate the wavelength and the frequency to the speed of the wave, which happens to be the speed of light in this situation. So as I introduced the quantum mechanics, introduction to quantum mechanics, I wanted to define it and sort of highlight some important properties. First of all, quantum physics is the branch that deals with small objects. And by small, we're talking about nuclear, atomic, in that realm, also subnuclear, quarks, etc. The quantization of various entities at that level as well, including energy and angular momentum. You will find that the electron in a hydrogen atom is allowed only certain energy levels, or that hydrogen atom is allowed only certain energy levels as well as angular momentum. So it's very weird. Basketball, if you think about a basketball, it could have any energy and any angular momentum. But when we get that small, there's a quantization of the quantities that we don't really expect. And you'll see where this comes from. But this is what happens, is that the quantization says that only certain values are allowed and not a continuum of values. Like I said, with a basketball, it could have any speed, it could have any energy, it could be spinning at any angular velocity, it doesn't matter. But with the hydrogen atom, the electron in the hydrogen atom, any types of atom, we see that only certain values are allowed, not this continuum that we're used to typically. We see this with basic charge as well as energy and angular momentum. And what I will bring up as we look towards like grand unified theory, there's what we establish as the correspondence principle, that if there's anything going on at a subatomic level, there's a correspondence at some point. It melds at the classical limit where we observe it every day. At this classical limit, quantum mechanics becomes the same as classical physics. So at some level, there's an approximation that happens that what we observe at a subatomic level is consistent with what we observe at a classical level, right? An everyday Earth sort of level, with some approximations. And we saw that with relativity as well. The first place we saw this, and it was really weird, Max Planck was studying radiating bodies. And what he saw was that he earned his Nobel Prize for it in 1918. And what he saw is that the emission curve for a radiating body, and what you can see here is there's a wavelength, and you may think about like the light bulb or the sun or other stars, etc. They have some sort of heat that they radiate. There's radiation emitted by these objects, which corresponds to some sort of wavelength for that radiation. The intensity of that light is related to the wavelength. And the hotter an object, the greater the intensity, but also the characteristic wavelength for that radiating body becomes, this peak here, changes for hotter objects. And we see that there's this black body radiation curve. And we can calculate this maximum value, this characteristic wavelength. A hotter body will have a smaller characteristic wavelength than a cooler body, and this is true. What Planck won his Nobel Prize for was deriving this emission curve by modeling a black body as a large number of oscillators whose energy states. So I think about a star. I think about it having just a bunch of springs in it, an oscillator. And the energy of those springs as they oscillate are given by very specific quantified values. And this was not anticipated at all, and that's why Planck won his Nobel Prize. This was such a revolutionary departure from classical physics that Planck himself did not even want to accept these results. That energy states are not continuous. At a classical level, we can have energy, any energy. It's a continuum. But when we look at black body emission and this radiation, it's not continuous. There's only quantized values allowed. And so we have this quantization of light, Further evidence of this was presented by the emission and absorption spectra of atoms. And what you see here, I brought this up here from OpenStax. This is the emission or atomic spectra of oxygen, an oxygen atom. And you can see here across all the colors, there's certain ones that are emitted right here. If the oxygen atom just emitted a whole bunch of energy and it wasn't quantized, we would have an equal amount across the whole spectrum. But we can see that instead we get these lines in here, very specific lines corresponding to specific energies of that light. So electromagnetic waves associated with electrons transitioning between energy levels in individual atoms and molecules is quantized. This was not something that was expected, but is true. And you can see the picture up here. There's when an atom transitions between states, photons are emitted, and depending on those energy levels, it determines the energy of that light being emitted. We call this atomic spectra, emission spectra, or line spectra. And the important characteristics of these spectra is that they are discrete. Okay, you can see that in here. Here's one. They're very discrete. They're very precise values. And so what we see is there's this quantization of light energy. When there's a transition between states, whether it be an oscillator or in an atom, the energy emitted is quantized in units related to the frequency of the light. So you can see the frequency is in here. Delta E equals H delta F. H is a very important constant in the cosmos, Planck's constant. It's 6.626 times 10 to the negative 34th joules times seconds. So when you use that constant, you can have that there. It will be given to you on an equation sheet, etc. And then all we have to do is know the frequency of the light, and then we know the energy of the light. We just multiply by Planck's constant. Very interesting. Quantization of energy resembles a standing wave. So that when I was talking about why energy is quantized, to quell your curiosity on this, why is it quantized? Here's the shortest story, is that this energy resembles a standing wave. When you think about a standing wave on a string, in order to have nodes and antinodes, that length has to be very specifically related to the wavelength of that wave, right? It's standing wave. And so that's why we get these specific values, and you can liken it to the harmonics described by integers for standing waves, like with musical instruments. And that's the reason why it's quantized. We're going to look more at the standing wave stuff as we move towards atomic physics. But I wanted to just pause for a second and use this equation. This equation is pretty easy to use, and you can see that I just did E equals HF. It says blue light is 445 nanometers. Determine the frequency of the light. Determine the energy of the photon of the light in joules and in electron volts. So let's work on the first part here. Determine the frequency of light. Well, I don't know the energy, so I'm going to remind you that we do know the speed of light, and we're given the wavelength of the light, and the speed of light is related to the wavelength of the light and the frequency. So if I want to find the frequency, I would take C and divide by lambda. So pretty easy there, 299,792,458 meters per second. And I divide by the 445 times 10 to the negative 9th meters. You can see I get 1 over seconds. And the frequency of this, you can put it through your calculator, you get to be 6.74 times 10 to the 14th hertz. So that would be the frequency of it. In order to find part B, we need the frequency. Frequency, energy equals H times the frequency. I'm going to do this though. H times the frequency. I'm going to remember that the frequency is C over lambda, so you could plug that in, HC over lambda. So if I'm solving for the energy of this photon in joules, we'll do 6.626 times 10 to the negative 34th joules times seconds. I'm going to multiply that by C, 299,792,458 meters per second, and I'm going to divide by the wavelength, 445 times 10 to the negative 9th meters. So we can see when that cancels through, we're going to be left with joules, and the energy in joules is 4.4656 times 10 to the negative 19th joules. If I want to convert this to electron volts, I know that 1 electron volt is 1.6 times 10 to the negative 19th joules. That's the basic charge, right? So I'll divide this by the basic charge, and I get 2.791 EVs. That's the energy of blue light with a wavelength of 445 nanometers. Pretty straightforward equation to use.